Why does the universe have a speed limit, and why, of all things, is that limit the speed of light? This question strikes at the core of physics and challenges our understanding of reality itself. At first thought, speed seems like something that should be limitless. If you can go fast, why not faster? If you can cross great distances, why should there be an upper bound? Yet the universe enforces a strict ceiling, and that ceiling is not random. It is precisely the speed of light. This speed is not just a number, but a principle built into the structure of space and time. It determines how information flows, how causality unfolds, and how the universe itself operates. Without this limit, paradoxes would arise, laws of energy would break, and the order of events could collapse into chaos. The speed of light is not merely fast, it is fundamental, a constant against which the entire cosmos is measured, revealing that reality itself has rules that nothing can disobey. The speed of light is one of those numbers that seems simple at first, but the more you think about it, the more astonishing it becomes. At about 300,000 kilometers per second, or roughly 186,000 miles per second, it is the fastest speed we know of in nature. To put this in context, a commercial jet flying at around 900 kilometers per hour would take more than 44 hours to circle Earth, while light could do it 7.5 times in just 1 second. That kind of velocity defies normal human imagination, because our brains evolved to understand running speeds, animal chases, or moving vehicles, not something that could cross the span of continents in the tiniest fraction of an instant. Even everyday astronomical distances highlight just how fast this benchmark really is. The Moon, orbiting some 384,000 kilometers away from us, is reached by light in just over 1 second. The Sun, sitting about 150 million kilometers away, sends its light that bathes Earth in a travel time of only about 8 minutes. In cosmic terms, those distances are practically nothing. Yet already we see how light allows us to bridge them in moments. When we look beyond the Sun, the scale grows more dramatic. Light takes more than 4 years to reach us from Proxima Centauri, the closest star beyond our solar system. That means when we gaze at that star, we are seeing it not as it is now, but as it was 4 years ago. The farther into space we look, the deeper into the past we are peering, because light, even at its incredible speed, takes time to arrive. This is part of what makes the speed of light not just a convenient number, but the cosmic benchmark. It is the standard that allows us to measure vast distances in terms of how long light takes to travel them. Instead of saying something is trillions of kilometers away, astronomers use light years, the distance light travels in a single year, which is nearly 9.5 trillion kilometers. By defining distance in terms of light's journey, we are acknowledging that this speed is woven into the way we perceive and navigate the cosmos. Light's velocity is not just about how fast photons move, it is about how information travels across the universe. When light from a star reaches us, it brings with it the story of that star's past, carrying the information across unimaginable gulfs of space. But why does light, in particular, become the cosmic yardstick? It is not simply because it is the fastest thing we have measured. It is because light represents the upper limit of how information and energy can move through space-time. Unlike sound waves or water ripples, light does not need a medium to travel through. It is self-sustaining, an electromagnetic wave that carries itself forward. This independence means that whether in the vacuum of space or across the emptiness between galaxies, light always moves at the same maximum speed. That constancy, regardless of the observer's motion or direction, makes it unique. If you were on a train moving at 100 kilometers per hour and you threw a ball forward at 20 kilometers per hour, someone standing on the ground would see the ball moving at 120 kilometers per hour. That makes sense in everyday terms. We add velocities together. But with light, the rules change. No matter how fast you move, if you shine a flashlight, the beam still leaves at 300,000 kilometers per second, and every observer measures it the same way. Even if two people are rushing toward each other at high speeds, the light from one's flashlight doesn't appear to the other as moving faster than the cosmic constant. This is why light's speed is not just another measurement, it is the ruler of spacetime itself. It stays fixed, unchanging, no matter what, which makes it the perfect cosmic benchmark. This peculiarity is also why the speed of light is not just a measurement of velocity, but a fundamental constant of nature, denoted by the symbol c. In equations across physics, from Einstein's famous to Maxwell's electromagnetic theory, this constant appears again and again. It is not negotiable, not relative, not a matter of perspective. The value of is baked into the structure of the universe, setting the rules by which energy, mass, and information operate. Its constancy across all frames of reference is the very reason relativity exists, because physics needed a new framework to make sense of a universe where this speed never changes. And so, light's incredible velocity is more than just a number. It is the dividing line between what can happen and what cannot. Everything in our daily lives is measured against it, whether we realize it or not. Our navigation of the stars, our understanding of distance, and our perception of time are tied directly to how fast light travels. It is the cosmic messenger bringing us the history of the universe, limited only by the fact that it cannot go any faster. Its speed forms a boundary wall for reality itself, defining the very structure of spacetime and giving us the most profound speed limit of all. Einstein's special theory of relativity, introduced in 1905, fundamentally transformed how we understand space, time, and motion. Before Einstein, the prevailing assumption was that velocities simply added together. If a train moved at 100 kilometers per hour and someone on it threw a ball at 20 kilometers per hour, an outside observer would see the ball traveling at 120 kilometers per hour. This made sense in everyday experiences, but broke down at extreme velocities. Maxwell's equations for electromagnetism already suggested that light traveled at a fixed speed, regardless of the observer's motion, which created a glaring contradiction. Einstein's insight resolved this by proposing that the laws of physics and the speed of light are the same for all observers, no matter how fast they are moving. This was revolutionary because it forced a reconsideration of the nature of space and time itself. In special relativity, time and space are no longer separate, immutable entities. Instead, they are intertwined into what we now call spacetime, a four-dimensional fabric in which the speed of light acts as a universal limit. One of the most astonishing consequences is that as objects move faster, time for them slows down relative to a stationary observer, a phenomenon known as time dilation. This is not a trick of perception. It is a fundamental feature of reality confirmed by countless experiments, including precise measurements with atomic clocks flown on airplanes or placed in satellites. By tying time and space to velocity, Einstein's theory set the stage for understanding why light speed is not just a number, but the ceiling for motion. Special relativity also introduced the concept that mass and energy are interchangeable, encapsulated in the famous equation E equals mc squared. This relationship implies that as an object's speed increases, its effective energy increases, and with it, its relativistic mass. This rising mass makes further acceleration progressively harder. No matter how much force you apply, an object with mass will never reach the speed of light because it would require infinite energy to do so. Here, Einstein's theory explains why the speed of light acts as a strict upper limit. It is not just a property of light itself, but a limit dictated by the relationship between energy, mass, and motion. Another profound implication of special relativity is that simultaneity is relative. Two events that appear simultaneous to one observer might occur at different times for another observer moving at a different velocity. This shows that time is not universal but flexible, adjusting depending on speed and position in spacetime. This insight dissolves the classical notion of absolute time and introduces a reality where the speed of light is the ultimate constant against which all motion and temporal perception are measured. Without a universal speed, the synchronization of events would break down, making causality unreliable. Special relativity also gives rise to the phenomenon of length contraction. As an object moves closer to the speed of light, distances along the direction of motion shrink from the perspective of a stationary observer. Combined with time dilation, this means that space-time itself is elastic, stretching and contracting to ensure that no object ever exceeds the cosmic speed limit. These effects are not noticeable in our everyday lives because they become significant only at velocities approaching light speed, but they dominate the behavior of particles in high-energy physics experiments and in the realm of astrophysics. Einstein's formulation also allowed physicists to understand the propagation of light as more than a wave phenomenon. It tied light's behavior directly to the structure of space-time. By establishing that nothing with mass can reach the speed of light without requiring infinite energy, special relativity sets the foundation for modern physics. It shows that the speed of light is not just an observational artifact, but a consequence of how the universe is constructed. It underpins everything from particle accelerators to GPS satellite systems, which must account for relativistic effects to maintain accuracy. Special relativity also leads naturally to general relativity, where the concepts of space and time are extended to include gravity. In both frameworks, the speed of light remains the ultimate limit, governing the maximum rate at which information and influence can propagate through the cosmos. Even in the presence of strong gravitational fields, no signal or object with mass can outpace light. This universality underscores how deeply the limit is embedded into reality. It is a law written into the fabric of existence, not a mere technological or observational constraint. Experiments over the past century have confirmed special relativity to extraordinary precision. High-energy particle collisions, atomic clock comparisons, and measurements of cosmic rays all demonstrate that as particles accelerate closer to light speed, their energy grows and their velocity asymptotically approaches, but never surpasses it. No exception has ever been observed, reinforcing that the limit is fundamental. It is not a boundary that could be overcome with enough ingenuity or machinery. It is the structure of reality itself asserting that nothing with mass can outrun the cosmic speed. Einstein's special relativity not only reshaped physics, but also reshaped our understanding of the universe. It replaced the intuitive Newtonian idea of absolute space and time with a dynamic, interwoven space-time where the speed of light is the ultimate constraint. This single insight explains why nothing can move faster than light, why energy grows without bound as speeds increase, and why time and space themselves adjust to preserve this limit. Light speed is baked into the universe's operating system, setting the rules for everything from subatomic particles to galactic motion, making it the defining constant that governs reality. Relativity establishes the idea of a cosmic speed limit with absolute clarity. Nothing that possesses mass can ever reach or exceed the speed of light. Unlike our everyday experiences, where speed seems like a relative measure that can be increased indefinitely with enough effort, the universe imposes a hard ceiling. This is not an arbitrary rule or a limitation of our technology. It is a fundamental property of spacetime itself. Any object with mass, no matter how small or dense, requires more and more energy to accelerate as it approaches this ultimate speed. The closer it gets, the more dramatic the energy demand becomes, creating an insurmountable barrier at the very moment it would theoretically reach light speed. The key idea behind this limit is embedded in the relationship between mass, energy, and velocity. As an object accelerates, its relativistic mass increases, meaning it behaves as if it becomes heavier in terms of the energy required to push it faster. For instance, a spacecraft traveling at half the speed of light requires significantly more fuel than one moving at everyday velocities, but the difference is manageable. However, as the velocity climbs closer to light speed, the energy requirement escalates drastically, approaching infinity. In practical terms, no conceivable propulsion system could supply infinite energy, making light speed an unattainable boundary for any particle with mass. This cosmic speed limit also ensures the preservation of causality, the principle that cause precedes effect. If mass could surpass light speed, events could be observed out of sequence, creating paradoxes where an effect might occur before its cause. This would undermine the very structure of physical law and make prediction and understanding of the universe impossible. By enforcing the speed of light as an ultimate boundary, relativity guarantees that information and influence travel in a consistent, orderly fashion, preserving the logical sequence of events throughout space and time. From a mathematical standpoint, the equations of relativity show that as velocity approaches light speed, the factor by which time slows down and distances contract becomes infinite. Time dilation stretches to extremes, and length contraction compresses distances along the direction of motion, effectively warping space-time around the object. No amount of acceleration can overcome this effect. Space-time itself adjusts to prevent a massive object from ever reaching the cosmic speed limit. These results are not speculative. They have been repeatedly confirmed in laboratory settings, particularly with particle accelerators, where subatomic particles are propelled at speeds extremely close to light speed. Despite enormous energy inputs, they never reach or exceed it. This limitation applies universally, regardless of the type of particle or the method of propulsion. Whether we are dealing with protons, electrons, or entire spacecraft, the principle holds. Even objects moving through the near vacuum of space, where frictional forces are negligible, are bound by the same cosmic law. Light speed is not just the fastest that light can travel, it is the fastest that anything, anywhere, at any time, can travel through the universe if it has mass. It is the ultimate speed limit, imposed not by machinery, friction, or environmental factors, but by the very structure of reality. The cosmic speed limit also has profound implications for our understanding of energy. If an object could somehow reach light speed, its mass would become infinite, and the energy required would also become infinite. In relativity, energy and mass are deeply interconnected. Accelerating an object increases both its kinetic energy and its effective mass. Near light speed, these quantities grow exponentially, creating a feedback loop that makes surpassing the speed of light impossible. This isn't a practical limitation, it is a fundamental one. No technological innovation or engineering breakthrough could circumvent this law because it is embedded in the very equations that define the universe. Even thought experiments reinforce this idea. If a spaceship were to somehow approach light speed, the crew would experience time dilation, seeing the rest of the universe speed up around them. Distances in the direction of travel would shrink due to length contraction. While these effects make the journey to distant stars seem shorter from the traveler's perspective, they never allow the spaceship to exceed light speed. From the perspective of an outside observer, the ship would asymptotically approach the speed of light but never reach it. This universal agreement across perspectives is a hallmark of relativity. The speed of light is invariant and unbreakable. The cosmic speed limit also has implications for the universe's large-scale structure and communication. Galaxies, stars, and cosmic signals all interact within the constraints of this maximum velocity. Even gravitational influences, such as waves produced by colliding black holes, propagate at light speed, confirming that this limit governs not just material objects, but also the transfer of energy and information. In other words, the speed of light defines the ultimate rhythm of cosmic events, setting the pace for everything from particle interactions to galactic dynamics. The cosmic speed limit is a universal law that no particle with mass can violate. It emerges naturally from the principles of relativity, supported by both theoretical reasoning and experimental evidence. It preserves causality, ensures consistent laws of physics, and shapes the flow of energy and information across the universe. The speed of light is not just a limit for light itself. It is the ultimate velocity boundary embedded into the very fabric of spacetime, defining the maximum pace at which the universe can operate. One of the most fascinating consequences of relativity is the intimate connection between energy, mass, and motion. In everyday life, we tend to think of mass as fixed. A car has a certain weight. A person has a certain mass. But relativity shows that mass is not entirely constant when objects move at high speeds. As an object accelerates closer to the speed of light, its effective mass increases. This is often referred to as relativistic mass, and it is a measure of how much energy is required to continue accelerating the object. In essence, the faster an object goes, the heavier it becomes in terms of the energy you must supply to make it go even faster. This relationship between energy and mass is most famously captured in Einstein's equation E equals mc squared, which demonstrates that mass itself is a form of energy. But when an object is in motion, the energy it possesses isn't just static. It includes kinetic energy, which grows dramatically as velocity increases. At everyday speeds, the contribution of motion to mass is negligible, which is why Newtonian physics works so well in our daily experience. A car moving at 100 kilometers per hour doesn't noticeably increase in mass compared to when it's at rest. However, as velocities approach a significant fraction of the speed of light, relativistic effects dominate, and even tiny increases in speed require enormous amounts of energy due to the corresponding increase in effective mass. To visualize this, imagine trying to push a particle in a high-energy accelerator. At low speeds, it responds predictably to applied force, accelerating smoothly. But as it approaches the speed of light, each additional push adds less velocity than expected, because its energy is increasingly being converted into increasing mass rather than speed. This explains why particle accelerators like the Large Hadron Collider require such staggering amounts of energy to propel subatomic particles close to light speed. Even when scientists pour in extraordinary amounts of energy, the particles get ever closer to the speed of light, but never reach it, because the energy increasingly manifests as increased relativistic mass rather than as additional velocity. This growth of effective mass with speed also creates a natural barrier to faster-than-light travel. Because the mass grows without limit as an object nears light speed, the amount of energy required to continue accelerating also trends toward infinity. No practical or theoretical energy source could ever supply infinite energy, making light speed an unattainable limit for massive objects. This isn't just a quirk of mathematics. It is a physical reality embedded into spacetime. Mass itself becomes a resistance to acceleration, and the faster you try to move, the stronger the universe pushes back in the form of growing inertial mass. The energy-mass relationship also has profound implications for high-speed cosmic phenomena. Cosmic rays, for example, are subatomic particles moving near light speed, often accelerated by supernovae or other astrophysical events. These particles possess energies so high that their effective masses are hundreds of times larger than their rest mass. In other words, the faster they move, the more energy they carry, and this energy manifests as a relativistic increase in mass that prevents them from reaching or surpassing light speed. Without this mechanism, the universe would be a very different place, potentially allowing particles to travel faster than causality permits and creating paradoxes in the sequence of events. Another way to understand this concept is through the analogy of pushing against resistance that grows with speed. At low velocities, the resistance is minimal and acceleration is relatively easy. As speed climbs, the resistance grows exponentially, making each incremental increase in velocity require vastly more energy. In relativistic terms, this resistance is the effective mass increasing with velocity. It acts as nature's safeguard, ensuring that nothing with mass can ever break the cosmic speed limit. The universe enforces this rule through energy itself, embedding the restriction into the fundamental physics rather than leaving it as a mere observational pattern. Even for hypothetical spacecraft designed to travel near light speed, this energy-mass relationship presents formidable challenges. To accelerate a massive object close to light speed would require energy comparable to the output of entire stars over long periods. And yet, even as we pour in energy, the spacecraft's speed asymptotically approaches the speed of light without ever reaching it. This demonstrates how intimately energy, mass, and velocity are linked, and how the universe uses this relationship to enforce the cosmic speed limit. In this sense, the energy-mass relationship is both a law of physics and a protective mechanism, preserving the consistency and causality of the universe. As an object accelerates, its effective mass grows, and the energy required to continue accelerating rises steeply. This connection is why no object with mass can ever attain light speed. The universe converts additional energy into mass rather than velocity, creating an insurmountable barrier. The principle underscores the unity of energy, mass, and motion, showing that the faster you try to go, the more resistance the universe imposes. It is not a technological limitation or a temporary obstacle, but a fundamental property of reality, ensuring that the cosmic speed limit is absolute and unavoidable. One of the most striking consequences of relativity, when combined with the relationship between energy and mass, is the infinite energy problem. This issue is straightforward in theory, but staggering in implication. As an object with mass accelerates closer to the speed of light, the amount of energy required to continue its acceleration increases without limit. At first glance, this might seem like a mere inconvenience. After all, if you have a powerful enough engine, couldn't you just keep pushing? But the mathematics of relativistic motion reveal a far more insurmountable barrier. The energy requirement does not just increase linearly, it grows asymptotically, meaning that as velocity approaches light speed, the energy needed approaches infinity. This makes reaching light speed fundamentally impossible for any massive object. To visualize this, consider the formula for relativistic kinetic energy. In classical mechanics, kinetic energy increases proportionally with the square of velocity. Double the speed, roughly quadruple the energy. But in relativity, kinetic energy increases far more dramatically as velocity nears light speed because the object's relativistic mass increases. This growing mass requires exponentially more energy for each additional increment in speed. Even if you could somehow harness all the energy produced by the sun for thousands of years, it would still be insufficient to propel a massive object to light speed. The energy demand outpaces any conceivable resource, demonstrating that light speed is not merely difficult to reach, it is physically unattainable. This infinite energy requirement is not an abstract mathematical curiosity. It has real-world implications in particle physics. In particle accelerators like the Large Hadron Collider, protons are accelerated to speeds extraordinarily close to light speed. Despite the enormous energy supplied, equivalent to millions of times the kinetic energy of a fast-moving car, the protons never reach light speed. As they get closer, additional energy increasingly goes into increasing their effective mass rather than adding velocity. The experiment provides direct confirmation of the infinite energy barrier. No matter how much energy is applied, the particles approach but never reach the cosmic limit. The infinite energy problem also highlights why everyday intuition fails at high velocities. In ordinary life, we rarely encounter situations where energy requirements grow non-linearly with speed. Driving a car or throwing a ball, the energy we expend results in predictable increases in velocity. But in the relativistic domain, as speed climbs to a significant fraction of light speed, each additional increment in velocity requires an energy input that quickly becomes unimaginably large. The universe responds to our attempts to accelerate mass by demanding more energy, ensuring that the speed limit remains unbroken. This principle has profound implications for hypothetical space travel. Consider a spacecraft designed to journey to the nearest star system at near light speed. Even with a propulsion system far beyond current technology, accelerating a craft with significant mass to even 90 or 99% of light speed would require energy amounts comparable to that emitted by entire stars over long periods. To attempt 100% of light speed would require literally infinite energy. The very fabric of reality imposes this ceiling, making interstellar journeys at or above light speed a physical impossibility, at least according to our current understanding of physics. The infinite energy problem is also tightly connected to the concept of massless particles. Photons, for example, travel at light speed precisely because they have no rest mass. Since they have no mass to increase as velocity increases, they do not face the energy barrier that massive particles encounter. This distinction illustrates why light speed is a unique threshold. It is achievable only for massless entities, while everything with mass is constrained by the unbreakable wall of infinite energy. Even thought experiments involving hypothetical superaccelerators cannot bypass this limitation. If one imagines a machine capable of producing an infinite amount of energy, it still cannot accelerate a massive object to light speed, because the equations themselves dictate that the energy grows without bound as the speed approaches the limit. This shows that the infinite energy requirement is not just a technological hurdle, it is a fundamental law of nature. It is an intrinsic part of the universe's structure, ensuring that massive objects remain forever below the ultimate speed. The infinite energy problem also has philosophical implications. It suggests that the universe is not a playground where anything is possible. Even with perfect knowledge and unlimited technology, certain boundaries are insurmountable because they are encoded into the very rules of physics. The energy barrier is a manifestation of nature's way of preserving consistency and causality, preventing violations that could undermine the order of events across space-time. Light speed is therefore not simply a measurement of velocity. It is a physical principle that governs the limits of motion, energy, and mass in the universe. Reaching light speed is impossible for anything with mass, because doing so would require infinite energy. This is not a limitation of imagination, technology, or engineering. It is a consequence of the universe's fundamental laws. The faster an object moves, the more its energy increases, and as it approaches light speed, the energy demand grows without bound. Nature imposes this limit to preserve the structure of space-time, maintain causality, and ensure that the cosmic speed limit is absolute. The infinite energy problem is the ultimate reason why no massive object can ever surpass or even reach the speed of light, making it the universal speed ceiling embedded in reality itself. One of the most mind-bending and counterintuitive consequences of traveling at speeds approaching the speed of light is time dilation. In our everyday experiences, time seems absolute and uniform. A minute passes the same for everyone, regardless of where they are or how fast they are moving. Relativity shatters that notion. When an object moves at a significant fraction of the speed of light, time for that object itself slows down relative to a stationary observer. This is not an illusion or a trick of perception. It is a physical reality that has been experimentally verified countless times. Atomic clocks flown on high-speed jets, satellites in orbit, and particles in accelerators all experience measurable differences in elapsed time compared to clocks at rest. The mechanism behind time dilation lies in the relationship between motion and spacetime. As an object accelerates, the intervals between events, ticks of a clock, beats of a heart, or atomic vibrations, stretch when observed from a stationary frame of reference. From the perspective of someone traveling at near light speed, everything aboard the moving vehicle appears normal. Their clocks tick normally, their heartbeat feels ordinary, and they experience time as usual. However, to an outside observer, time aboard the fast-moving object appears to slow dramatically. This means that the traveler ages more slowly relative to people who remain stationary. The faster they move, the greater the effect, with time theoretically stopping entirely at light speed, though massive objects can never reach that limit. A striking implication of time dilation is often illustrated with thought experiments involving interstellar travel. Imagine a spaceship journeying to a distant star at a velocity close to the speed of light. For the crew aboard the ship, the journey might seem to take only a few years because time aboard the spacecraft moves more slowly. Yet, for observers back on Earth, decades or even centuries could pass. Time dilation shows that motion is not just a spatial phenomenon, but also temporal. Moving faster fundamentally alters the passage of time itself. This effect is not merely theoretical. It has been repeatedly confirmed in high-energy physics experiments. Particles known as muons, which decay quickly at rest, live significantly longer when traveling near light speed due to time dilation, reaching detectors that they otherwise could not. Time dilation also has practical consequences in modern technology. The Global Positioning System, GPS, provides a concrete example. Satellites orbiting Earth experience both special and general relativistic time effects. Their velocities induce time dilation, slowing their onboard clocks relative to clocks on Earth, while the weaker gravity at orbital altitudes causes general relativistic time to speed up slightly. Engineers must account for these effects, or GPS systems would accumulate errors of kilometers in positioning every single day. This real-world example demonstrates that time dilation is not just a theoretical curiosity, but a measurable and essential feature of our universe. The effect becomes dramatically more pronounced as velocities approach the speed of light. At half-light speed, time aboard a spacecraft might run at roughly 87% the rate experienced by a stationary observer. At 90% of light speed, that drops to about 44%. At 99%, time aboard slows to just 14% of normal passage. These ratios are not linear. They escalate as velocity nears the universal limit. This asymmetry explains why relativistic effects are negligible in everyday life, yet dominate in high-velocity cosmic events or particle physics experiments. Time dilation also fundamentally reinforces the cosmic speed limit. If an object could somehow reach light speed, time for that object would theoretically stop entirely. This is why no massive object can ever attain light speed. As the velocity increases, not only does energy approach infinity, but the flow of time also slows asymptotically, making light speed an unreachable barrier. Massless particles, such as photons, naturally exist at this limit. They experience no passage of time in the conventional sense, which explains how light can traverse vast distances across the universe without experiencing the centuries or millennia that pass for external observers. In addition to its physical consequences, time dilation challenges our philosophical understanding of reality. It implies that the passage of time is not a universal backdrop, but a relative experience, dependent on motion and frame of reference. Two observers moving at different velocities will disagree on the duration of events, yet both perspectives are equally valid within their own frames. This relativity of time is one of the most profound lessons of Einstein's theory, reshaping our understanding of reality and forcing us to abandon the Newtonian idea of absolute, uniform time. Time dilation is not merely a theoretical curiosity reserved for textbooks or thought experiments. It is a tangible, experimentally verified phenomenon that occurs whenever velocities approach the speed of light. It illustrates how motion at extreme speeds warps the flow of time, slowing it for the traveler, while leaving the external universe ticking at its usual pace. This effect, combined with length contraction, mass energy growth, and the infinite energy barrier, forms a comprehensive framework explaining why light speed is not just a number, but a fundamental limit embedded in the nature of spacetime itself. Time dilation is one of the universe's clearest signals that at high velocities, reality behaves in ways that defy common intuition, revealing a cosmos governed by absolute, immutable laws. Length contraction is one of the most fascinating consequences of Einstein's theory of relativity, demonstrating that space itself is not absolute, but depends on motion. As an object moves closer to the speed of light, distances measured along the direction of its motion appear shorter from the perspective of a stationary observer. This effect, known as length contraction, is a natural complement to time dilation and is directly tied to the way space-time responds to high velocities. While time slows for the traveler, distances in the direction of travel compress, meaning that space itself is squeezed from the viewpoint of an outside observer. To visualize this, imagine a spacecraft racing past Earth at near light speed. To astronauts aboard the ship, the distance to a star or a planet feels normal. They experience no physical compression of the ship or the space around them. However, for someone watching from a stationary frame on Earth, the distance the ship has to traverse is significantly shorter than it would be if the ship were at rest. This contraction grows more pronounced the faster the spacecraft moves, becoming extreme as velocity approaches light speed. The effect is a direct consequence of the interdependence of space and time established in relativity. The faster an object moves, the more space-time itself adjusts to preserve the cosmic speed limit. Length contraction also helps explain why near-light speed travel seems more feasible from the traveler's perspective than from an external observer's viewpoint. For instance, a journey to a star system that would take decades at conventional speeds might feel far shorter to those on board a relativistic spacecraft because distances in their direction of travel are contracted. However, from the standpoint of someone on Earth, the same journey still covers the full, uncontracted distance, taking much longer in real time. This divergence between experienced time and contracted distance is a vivid illustration of how motion at relativistic speeds fundamentally warps our understanding of space and time. Experimental evidence for length contraction is compelling, though indirect, because observing macroscopic objects moving near light speed is impractical. high-energy particle experiments provide clear confirmation. Subatomic particles traveling close to light speed pass through materials in ways that imply contracted distances. Similarly, cosmic rays that penetrate Earth's atmosphere exhibit behaviors consistent with length contraction, traveling farther than would be expected if distances were not relativistically shortened. These results match precise predictions from relativity, reinforcing that length contraction is a real and measurable effect. Length contraction is not uniform in all directions. It occurs only along the direction of motion. Perpendicular distances remain unchanged, which helps preserve the overall geometry of space while enforcing the constraints of relativity. This directional contraction ensures that the speed of light remains constant for all observers. Without such spatial adjustments, observers in different frames would measure differing light speeds, violating the fundamental postulate of relativity. In this way, length contraction is not just a curious phenomenon. It is a necessary adjustment of spacetime to maintain the universal speed limit. When combined with time dilation, length contraction paints a universe that behaves very differently at extreme speeds. Time slows for the traveler, distances shrink along the direction of motion, and the traveler experiences a distorted but internally consistent view of space-time. Meanwhile, observers at rest see the traveler's clock running slower, and the ship covering the contracted distance faster than would be expected classically, but never faster than light. These relativistic effects work together seamlessly, enforcing the cosmic speed limit while preserving causality and the consistency of physical laws. Philosophically, length contraction challenges our intuitive notion of space as fixed and unchanging. It forces us to confront a reality in which space is flexible, responding dynamically to motion. The universe is not a static arena in which events occur. It is a malleable fabric that stretches and compresses depending on velocity. This perspective is crucial for understanding why massive objects can never reach light speed. As velocity increases, both space and time adjust in ways that make exceeding the universal limit impossible. For practical considerations, length contraction implies that high-speed travel fundamentally alters the distances experienced by travelers, even if they cannot perceive it directly. It also serves as a safeguard for the laws of physics, ensuring that the faster an object moves, the more space-time itself reshapes to prevent violations of the cosmic speed limit. Without this effect, causality could be compromised, and observers could detect faster-than-light motion, breaking the logical structure of events across the universe. In short, length contraction is a relativistic effect that complements time dilation, showing that space is not absolute but dynamically linked to motion. As objects move near the speed of light, distances along their direction of travel shrink from the perspective of stationary observers, enforcing the universal speed limit. This phenomenon, verified in high-energy particle experiments and cosmic observations, reveals the deep and non-intuitive ways the universe responds to motion. Space itself bends and adjusts, ensuring that nothing with mass ever reaches or surpasses the speed of light. Light occupies a unique position in the universe because it does not experience time or distance in the same way that objects with mass do. Unlike a particle or spacecraft, which always has a rest frame, a perspective from which it is stationary, light has no rest frame at all. If we attempt to imagine what it would be like to ride a beam of light, we immediately encounter a fundamental paradox. At the speed of light, time effectively stops, and distances in the direction of motion contract to zero. For photons, which are massless particles of light, the concepts of time and space as we understand them lose all meaning. In a sense, from the photon's perspective, The universe is traversed instantaneously, no matter how vast the distance might appear to an outside observer. This property of light stems directly from the postulates of special relativity. One of Einstein's fundamental insights was that the speed of light is constant in all inertial frames of reference. For any observer, whether stationary, moving slowly, or moving near light speed, light always travels at the same maximum velocity. This invariance has profound consequences. For a particle with mass, approaching this speed leads to time dilation and length contraction, but a massless particle, like a photon, exists entirely at this speed. Its journey across the universe is fundamentally different from anything that has mass. It does not experience the passage of time, and the distance it crosses is effectively collapsed in its own frame. Because light lacks a rest frame, it challenges our intuitive understanding of motion and causality. While we, as observers, see photons crossing immense cosmic distances over years, decades, or even millennia, from the photon's perspective, the emission and absorption are effectively simultaneous. In practical terms, this means that light can connect events across vast spacetime intervals without experiencing the progression of time between them. This is why photons emitted from distant galaxies, billions of light years away, can reach us, despite the unimaginable expanses of the universe. To light itself, the journey is instantaneous. The uniqueness of light also underpins many relativistic effects. Time dilation and length contraction become extreme as objects approach light speed, but photons exist entirely in the asymptotic limit. Time is frozen and distances are contracted to zero. This explains why light can travel at the universal speed limit without violating the infinite energy problem that prevents massive objects from reaching the same velocity. Because photons have no mass, they do not require energy to accelerate to light speed. They are always traveling at it. This sets them apart from every other entity in the cosmos and reinforces the idea that light speed is not merely a numerical threshold, but a fundamental property of the universe that defines the behavior of massless particles. This concept also clarifies why the universe is observable to us the way it is. Photons act as messengers, carrying information from distant stars, galaxies, and cosmic events. Even though billions of years might pass from the perspective of an external observer, photons themselves do not experience that passage of time. They are instantaneous bridges across space-time, making light a unique conduit for connecting events across the cosmos. Without this property, our perception of the universe, its age, structure, and evolution, would be fundamentally different. Furthermore, the absence of a rest frame for light explains why certain relativistic paradoxes cannot occur. Since there is no perspective from which light is at rest, concepts like experiencing faster-than-light travel or observing light from a stationary frame differently than from a moving frame are nonsensical. Light sets the standard for relativistic measurements. All observers measure the same speed for light regardless of their motion, and all other phenomena adjust in time and space to preserve this universal constant. In this way, light acts as the fundamental ruler of the cosmos, giving meaning to the structure of space-time while remaining unaffected by it in the way matter is. The implications of having no rest frame are profound. While we might think of motion and the passage of time as universal experiences, light exists entirely outside these constraints. Its existence demonstrates that space-time is flexible and relative, and that the ultimate limits of physics, such as the speed of light, are embedded in the very nature of reality. It is not that light moves fast compared to us. It is that light operates according to a different set of rules, one where the concepts of time and distance collapse into a unique, invariant mode of existence. In summary, Light's lack of a rest frame makes it fundamentally different from everything with mass. Photons experience no passage of time and no distance in their direction of travel, existing entirely at the universal speed limit. This property allows light to traverse immense cosmic distances, transmit information across the universe, and define the structure of space-time itself. It is the ultimate benchmark for motion and the standard against which all relativistic phenomena are measured, making light not only unique but central to the fabric of the cosmos. The principle of causality, the idea that cause precedes effect, is one of the most fundamental pillars of physics, and it is intimately tied to the cosmic speed limit set by light. In our everyday world, events occur in a clear sequence. A striking force causes a ball to roll. A spark ignites a flame. A signal triggers a response. This sequence seems so obvious that we rarely question it. However, when velocities approach or hypothetically exceed the speed of light, this seemingly straightforward relationship between cause and effect becomes vulnerable to paradox. Breaking the light speed barrier would allow information, matter, or signals to arrive before they were sent from some frames of reference, effectively reversing the order of events and undermining the consistency of reality itself. Relativity provides the mathematical foundation for why causality is preserved, as long as nothing travels faster than light. In special relativity, the interval between two events can be classified as time-like, light-like, or space-like. If the separation between events is time-like, all observers agree on the order of cause and effect. Light-like intervals are defined precisely by light speed transmission. Events connected by a photon still maintain causality because light speed is invariant. However, space-like intervals, where a hypothetical signal travels faster than light, allow different observers to disagree on the sequence of events. In such a scenario, what one observer sees as a cause, another could interpret as an effect, creating logical contradictions that are fundamentally inconsistent with the laws of physics. These potential paradoxes are not merely academic exercises. They illustrate why the light speed limit is essential for the coherence of the universe. Consider the classic tachyonic anti-telephone thought experiment. If a particle or signal could move faster than light, it might allow someone to send information backward in time. A message could theoretically arrive before it was sent, enabling violations of causality, such as preventing an action that caused the message in the first place. This produces a logical inconsistency akin to the famous grandfather paradox in time travel discussions. If an event in the past could be altered by future actions, the sequence of cause and effect would collapse, and the very notion of objective reality would become meaningless. The universality of causality is not only a philosophical concern, but also a practical one for physics. Many fundamental processes, chemical reactions, nuclear decay, and even the propagation of electromagnetic waves depend on the predictable order of cause and effect. If superluminal, faster-than-light motion were possible, these processes could be observed out of order in different reference frames. For instance, a decaying particle might appear to emit its decay products before the particle itself exists in certain frames, violating conservation laws and destabilizing the predictable structure of matter. The cosmic speed limit thus ensures that all physical processes remain logically consistent across the universe, preserving the integrity of natural law. Relativity's insistence that nothing with mass can exceed the speed of light is a safeguard against these paradoxes. It ensures that signals, forces, and interactions propagate within the light cone of space-time, a conceptual boundary delineating the limits within which cause and effect operate. Events inside the light cone are causally connected, while those outside are causally disconnected. If the speed of light were not the ultimate limit, light cones could be violated and events could influence each other in ways that break causality. In essence, the cosmic speed limit protects the universe from self-contradiction, enforcing a logical framework that applies consistently to all observers. Even hypothetical particles like tachyons, which are sometimes theorized to travel faster than light, illustrate the dangers of causality violation. According to theory, tachyons would allow effects to precede causes in certain frames, making them incompatible with our observed reality. No experimental evidence has ever detected such particles, and their existence would undermine the predictable sequence of events that physics relies upon. The absence of tachyons in nature reinforces the idea that the universe enforces light speed as a maximum precisely to maintain causality. Causality violations are also central to discussions of time travel. If massive objects or signals could move faster than light, one could theoretically construct scenarios where past events are influenced by future decisions, creating loops of self-contradiction. While science fiction often imagines such possibilities, the mathematical structure of relativity shows that these paradoxes are not merely unlikely, they are impossible under the physical laws governing mass and light. By maintaining the inviolate status of light speed, the universe ensures that cause and effect remain sequential and unambiguous, providing a stable framework in which physical phenomena unfold. The light speed limit is not just a boundary for velocity. It is a protector of logical order in the universe. Breaking this limit would lead to causality violations and paradoxes where effects could precede causes, undermining the predictable sequence of events on which all of physics relies. From the decay of subatomic particles to the transmission of information across the cosmos, causality ensures the coherence and consistency of reality. By enforcing the cosmic speed limit, relativity preserves this order, preventing paradoxes and maintaining the logical structure that underpins both natural law and our very understanding of time and space. The concept of information transfer is intimately tied to the cosmic speed limit because the propagation of any signal, whether it is a particle, an electromagnetic wave, or even a simple message, must obey the same fundamental constraints of spacetime. In essence, nothing can convey information faster than the speed of light without violating the principles of relativity. This limit is not merely a matter of technological capability, it is a structural feature of the universe. Any attempt to transmit information faster than light would immediately introduce contradictions in causality, allowing events to be observed out of order and breaking the logical fabric of reality. The transmission of information always involves a physical carrier. Whether it's photons traveling through a fiber optic cable, electrons in a circuit, or gravitational waves moving through space, information is fundamentally encoded in physical changes that propagate. According to relativity, these carriers are bound by the light speed ceiling. Signals can approach light speed asymptotically, but they cannot exceed it. If they could, then in certain frames of reference, the signal could arrive before it was sent, making it impossible to define a consistent sequence of events. This is a direct consequence of the spacetime structure defined by special relativity. Faster-than-light information transfer collapses the distinction between cause and effect. This limit applies universally to all forms of information, whether classical or quantum. For classical information, like radio waves, electrical impulses, or written messages, the carrier's speed is bounded by the physics of the medium and the immutable limit of light in vacuum. Even in idealized scenarios, no classical mechanism can propagate a signal faster than light. Attempting to do so would require violating the relativistic energy-momentum relationship, essentially demanding infinite energy, which is physically impossible. As a result, the universe naturally enforces the maximum speed at which information can propagate. In the realm of quantum mechanics, there is sometimes confusion due to phenomena like quantum entanglement. Entangled particles can exhibit correlations over vast distances instantaneously, leading to popular claims that information is transmitted faster than light. However, these correlations do not constitute usable information transfer. While measurements on entangled particles are instantaneously correlated, the results are fundamentally random until classical information is exchanged between observers. Any attempt to exploit entanglement to send messages faster than light fails because classical communication, bounded by the speed of light, is still required to interpret the entangled outcomes. Thus, even in the quantum domain, information transfer remains constrained by the universal speed limit. Gravitational interactions also conform to this boundary. When massive objects like stars or black holes shift position, the gravitational effects propagate at the speed of light, not instantaneously. This was confirmed experimentally through the detection of gravitational waves emitted by colliding black holes, which traveled at light speed to reach detectors on Earth. Had these signals moved faster, they could violate causality by allowing observers to detect the effects of an event before the event itself occurred. Nature, in this way, enforces the same information transfer limit across all fundamental forces and particles, ensuring a consistent causal structure. The impossibility of faster-than-light communication also has practical implications for technology and exploration. Any attempt to communicate with spacecraft at interstellar distances must respect the light speed limit. Messages to a probe near Proxima Centauri, for instance, take over 4 years to arrive because light is the fastest messenger available. Even if we could design perfect instruments or exploit exotic phenomena, the underlying physics prohibits sending information any faster. This reinforces the notion that the speed of light is not just a measure of how fast photons travel, but the maximum rate at which any influence, effect, or knowledge can propagate across the universe. The fundamental reason for this restriction lies in the structure of spacetime itself. Light cones define the regions of influence for events, indicating the maximum distance that any signal or information can travel over a given period. Anything outside the light cone is causally disconnected, meaning no cause and effect relationship can link those points. If information could exceed light speed, the light cone framework would collapse, and an event could influence points outside its causal domain. This would allow paradoxes, retrocausality, and logical inconsistencies to emerge, making the universe unstable and unpredictable. The light speed limit, therefore, is essential not only for motion, but for maintaining coherent communication and the integrity of information throughout space-time. Even in hypothetical scenarios, such as using wormholes or warp drives, the principles of relativity suggest that true faster-than-light information transfer is not achieved locally. Instead, these concepts rely on manipulating space-time itself to create shortcuts that allow information to effectively traverse large distances more quickly without locally exceeding light speed. Locally, the speed limit is never violated, preserving causality and the universal order. This reinforces the idea that information transfer cannot break light speed, even when the universe's geometry is bent or warped. Nothing, not even information, can travel faster than light without violating the fundamental laws of physics. This limitation is rooted in the structure of space-time, the energy requirements for transmission, and the preservation of causality. All physical carriers of information, classical or quantum, obey this restriction. Attempts to circumvent it would destabilize the logical sequence of events, allowing paradoxes and contradictions to emerge. By bounding information transfer to the speed of light, the universe ensures consistent cause and effect relationships, the stability of physical law, and a coherent framework for all interactions across spacetime. Among the more exotic ideas in theoretical physics is the concept of tachyons, hypothetical particles that, if they exist, would always travel faster than light. Tachyons were first proposed in the 1960s as a solution to certain equations in special relativity that mathematically allowed particles with imaginary mass. Unlike ordinary particles, which are constrained to move slower than light, tachyons would be fundamentally different. They could never slow down to or below light speed, and their intrinsic properties would always keep them superluminal. This idea immediately sparks fascination because it seems to offer a loophole to the universal speed limit, potentially enabling instantaneous communication or even violations of causality. The mathematics behind tachyons is intriguing but problematic. According to the relativistic energy-momentum relationship, a particle with real positive mass requires infinite energy to reach light speed, making superluminal motion impossible for ordinary matter. Tachyons, by contrast, would have an imaginary rest mass, meaning that as they lose energy, their speed would increase. This counterintuitive property flips our normal understanding of physics on its head. Instead of accelerating with more energy, a tachyon would decelerate as its energy increases. While this behavior is mathematically consistent within certain extensions of relativity, it defies every intuitive physical law observed in our universe. Tachyons also raise immediate concerns about causality. If such particles could interact with ordinary matter or carry information, they would permit signals to arrive before they were sent in some reference frames. This would create logical paradoxes akin to those discussed in the context of superluminal communication. Retrocausality, temporal loops, and violations of cause and effect could occur, undermining the stability of physical law. The hypothetical existence of tachyons would therefore not just challenge the cosmic speed limit, but threaten the very coherence of spacetime itself. It is no surprise, then, that most physicists regard tachyons as purely speculative, existing primarily as a mathematical curiosity rather than a physically realized entity. Experimentally, tachyons have never been observed, despite decades of searches and high-precision particle experiments. Scientists have examined high-energy collisions in accelerators and carefully monitored cosmic radiation for signs of superluminal particles, but no evidence has ever confirmed the existence of tachyons. Their absence in nature supports the principle that the speed of light is a fundamental limit, not a boundary that can be circumvented by exotic forms of matter. In a sense, the tachyon hypothesis highlights the consistency of relativity. Even when equations allow for hypothetical faster-than-light solutions, physical reality enforces the universal speed limit. Tachyons also appear in certain speculative areas of theoretical physics and science fiction, often as tools for exploring causality violations or instantaneous communication. In string theory, for instance, tachyonic modes sometimes emerge in mathematical formulations, indicating instabilities in certain configurations of strings rather than the existence of real superluminal particles. These modes are usually interpreted as signs that a theoretical system is unstable and will decay to a lower energy state, not as evidence of faster-than-light matter. Thus, tachyons serve as a theoretical probe for the limits of physics rather than a plausible candidate for real-world superluminal travel. Philosophically, the tachyon concept challenges our understanding of what is possible in the universe. While intriguing as a thought experiment, the notion that particles could move faster than light forces us to confront the consequences of violating fundamental constraints. The hypothetical properties of tachyons, imaginary mass, reversed energy-speed relationship, and the potential for temporal paradoxes demonstrate why light speed functions as a natural and inviolable barrier. By imagining tachyons, physicists gain insight into why the laws of physics are structured as they are, faster-than-light motion would destabilize both energy conservation and causality. In short, tachyons are purely theoretical particles that, if they existed, would always move faster than light and possess properties radically different from ordinary matter. While they are mathematically consistent within certain models, they remain speculative because they have never been observed and would create severe paradoxes if real. The study of tachyons underscores the robustness of the light speed limit. Even hypothetical entities cannot bypass the fundamental restrictions imposed by relativity without producing contradictions in energy, causality, and the structure of spacetime. They are a window into the theoretical edges of physics, illustrating why the cosmic speed limit is both necessary and unbreakable. Quantum entanglement is one of the most fascinating and widely misunderstood phenomena in physics, often cited in discussions about faster-than-light effects. Entangled particles are pairs or groups of quantum systems whose properties are interconnected in such a way that the state of one particle instantly correlates with the state of the other, regardless of the distance separating them. This spooky action at a distance, as Einstein famously called it, can seem to suggest that information is transmitted instantaneously between the particles, potentially violating the universal speed limit set by light. However, a closer examination of the physics reveals that entanglement does not, in fact, allow faster-than-light communication. The key to understanding why lies in the probabilistic nature of quantum mechanics. When two particles are entangled, measuring the state of one particle immediately determines the outcome of the measurement on the other particle. But these outcomes are fundamentally random. If Alice measures her particle and observes a particular result, Bob's corresponding particle will correlate with Alice's result, no matter how far apart they are. However, neither Alice nor Bob can control the outcome of their measurement. Because the results are inherently unpredictable, no usable information is transmitted between the two particles at the moment of measurement. The correlation is only revealed after the two parties compare their data through classical communication, which is limited to the speed of light. In practical terms, this means that entanglement cannot be used to send messages or signals instantaneously. Even though the state of the distant particle adjusts immediately upon measurement of its entangled partner, this adjustment does not constitute controllable information transfer. Without the ability to influence the outcome, no observer can encode a message into the entangled system to communicate faster than light. The process is akin to flipping two correlated coins in separate locations. The results match in a predictable way after the fact, but flipping them does not allow anyone to send a predetermined message across space. Experiments in quantum physics have confirmed these principles. Bell test experiments, which examine the correlations between entangled particles, show that the outcomes are consistent with quantum mechanics and exhibit correlations that defy classical explanation. Yet these experiments also reinforce that entanglement cannot transmit information faster than light. The correlations are observed only when data from both particles are compared using conventional communication methods, which obey the light speed limit. This consistency maintains the integrity of causality and confirms that relativity remains unviolated, even in the strange and counterintuitive quantum domain. Entanglement does allow some remarkable phenomena, such as quantum teleportation of states, but even here, the transfer of usable information still requires classical communication. Quantum teleportation does not transport matter or energy faster than light. It only transfers the quantum state from one particle to another while preserving causality. The process adheres strictly to the light speed constraint when it comes to conveying information or instructions, illustrating that quantum mechanics, while non-intuitive, does not provide a loophole for superluminal messaging. The misconception about faster-than-light communication via entanglement often arises from conflating correlation with transmission. While entangled particles show correlations that are instantaneous and seemingly distance-independent, these correlations are not controllable or predictable in a way that would constitute information transfer. Observers cannot use entanglement alone to influence outcomes or communicate messages. Classical signals are still required, and these signals cannot exceed the speed of light. This distinction is subtle but crucial for maintaining the consistency of physics. The persistence of this misconception is also tied to popular science discussions and media portrayals. Entanglement is often sensationalized as a way to send information instantly across the universe. But in reality, the universe's speed limit remains inviolate. Entanglement illustrates the non-local nature of quantum systems, the idea that distant objects can be fundamentally connected, but it does not overturn the constraints of relativity. In other words, quantum mechanics and relativity coexist harmoniously. Quantum entanglement reveals deep connections in nature without violating the cosmic speed limit. Quantum entanglement is a remarkable and experimentally verified phenomenon that creates instantaneous correlations between particles across vast distances. However, it does not allow faster-than-light communication because the outcomes of measurements are fundamentally random and uncontrollable. Any transmission of information still requires classical channels limited by the speed of light. Entanglement fascinates because it challenges intuition and hints at the interconnectedness of the universe, but it does not provide a loophole to surpass the ultimate cosmic speed limit. The universe preserves causality and the integrity of physical law, even at the quantum scale. Warp drives and wormholes represent some of the most imaginative and mathematically intriguing concepts in theoretical physics, offering potential ways to bypass the speed of light without violating the fundamental laws of relativity. Unlike traditional motion through space, which is constrained by the light speed limit, these ideas involve manipulating space-time itself. The central insight is that relativity restricts the local velocity of objects, but it does not forbid the expansion, contraction, or bending of space-time itself. By warping space-time, a spacecraft could, in theory, reach distant destinations faster than light would travel through normal space, all while never locally exceeding the cosmic speed limit. The warp drive concept, popularized by science fiction, was given a theoretical foundation by physicist Miguel Alcubierre in 1994. The Alcubierre drive proposes a mechanism in which a spacecraft is placed inside a warp bubble that contracts space in front of it and expands space behind it. Inside this bubble, the ship itself remains stationary relative to its local space-time, meaning it does not move faster than light in its immediate surroundings. Instead, the bubble of space-time carries the ship forward at effectively superluminal speeds relative to distant observers. This ingenious mechanism would allow journeys across light years in far less time than conventional propulsion could manage without violating relativity locally. However, the theoretical requirements for an Alcubierre warp drive are extraordinary and currently beyond practical reach. The equations demand exotic matter or negative energy density to stabilize the warp bubble, a form of matter that has never been observed in sufficient quantities, if it exists at all. Furthermore, the energy demands are enormous. Early estimates suggested it would require more energy than exists in the observable universe, though refinements to the theory have lowered the required amount somewhat. Even so, creating and sustaining such a warp bubble is currently far beyond human capability, making the idea a tantalizing theoretical construct rather than an engineering blueprint. Wormholes offer another theoretical pathway to bypass light speed limitations. A wormhole is a hypothetical tunnel through space-time connecting two distant points via a shortcut. In principle, traversing a wormhole could allow instant travel between points separated by vast distances without violating local relativistic constraints. Just as with warp drives, nothing inside the wormhole would exceed light speed locally. The shortcut exists because spacetime itself is reshaped. The Einstein-Rosen bridge, proposed as a solution to Einstein's field equations, is a type of wormhole that connects two points in spacetime. While mathematically plausible, traversable wormholes would require exotic matter to keep the tunnel stable and prevent collapse, just as with warp bubbles. The potential of warp drives and wormholes raises fascinating philosophical and physical questions. If we could manipulate spacetime itself, would the light speed limit still matter? Locally it would, but from a global perspective, the ship or traveler could traverse distances faster than light would in unwarped space. This distinction highlights the subtlety of relativity. The speed of light is a limit on motion through space, not on the expansion or contraction of space itself. These concepts, though speculative, illustrate that the universe's laws may allow pathways around the limitations we perceive, even if practical implementation remains far beyond current technology. Despite their allure, both warp drives and wormholes remain entirely theoretical. No experimental evidence confirms the existence of stable wormholes, and no known material or energy source could generate the negative energy densities required for a warp bubble. They exist primarily as mathematical solutions to Einstein's equations, highlighting what is possible within the framework of general relativity, rather than as technologies we can build today. Yet their study is valuable. They push the boundaries of theoretical physics, explore the limits of space-time geometry, and inspire new ways of thinking about motion, causality, and the structure of the cosmos. Science fiction has long embraced these ideas, imagining civilizations traveling across galaxies or communicating instantaneously via wormholes or warp drives. While these depictions are often exaggerated or simplified, they serve to popularize complex physics and spark inquiry into the limits of reality. The theoretical investigation of such possibilities is rigorous. Physicists use general relativity, quantum field theory, and energy constraints to test whether these ideas could, in principle, work, even if the practical hurdles are astronomical. Warp drives and wormholes offer tantalizing glimpses of how the universe's geometry might be manipulated to effectively bypass the speed of light without violating relativity locally. By expanding, contracting, or tunneling through spacetime, these concepts allow theoretical superluminal travel while preserving the light speed limit for matter and information in local frames. Though currently speculative and practically unachievable, they demonstrate the incredible flexibility of spacetime and the richness of Einstein's equations, hinting at possibilities far beyond conventional propulsion, while reinforcing the subtle distinction between local motion and global spacetime structure. Photons occupy a unique and essential role in the universe because they are fundamentally massless particles, a property that allows them to travel at the ultimate cosmic speed limit, the speed of light. Unlike objects with mass, which experience relativistic effects that prevent them from reaching or exceeding light speed, photons require no energy to accelerate to this limit. They are born traveling at this velocity, and their massless nature is precisely what permits them to do so. Without this unique characteristic, the transmission of light, electromagnetic radiation, and information across the cosmos as we know it would be impossible. The absence of rest mass in photons means that they do not experience the relativistic resistance that ordinary matter faces. When objects with mass accelerate toward light speed, their relativistic mass increases, demanding ever more energy to continue accelerating. Photons, having zero rest mass, bypass this constraint entirely. They cannot move any slower than light in vacuum. and they do not need any energy to maintain their speed. This property makes them perfectly suited to carry electromagnetic energy and information across vast cosmic distances, from the nearest lamp to the most distant galaxy. Their velocity is fixed, invariant, and consistent in every inertial frame, which is one of the cornerstones of special relativity. The behavior of photons also reinforces the structure of spacetime. Because they move at the universal speed limit, photons define the light cone for all events, establishing the causal boundaries of the universe. Every signal, force, or interaction that relies on light or electromagnetic radiation propagates within these boundaries, preserving the order of cause and effect. In this sense, photons are not just messengers of light, they are fundamental to the very structure of reality, acting as markers for the maximum rate at which any influence can propagate. Moreover, photons' masslessness explains why they experience no time or distance in the way that objects with mass do. From the photon's perspective, the emission and absorption of light occur simultaneously across any distance. Though observers in a stationary frame see photons crossing billions of kilometers, the photons themselves do not experience the passage of time, nor do they perceive the distance traveled. This unique quality is a direct consequence of being massless, making photons the natural entities to traverse the universe at light speed while preserving relativistic laws. The fact that photons can move at light speed also underpins many technologies and observations critical to humanity. Every form of visual perception, radio transmission, satellite communication, and astronomical observation relies on photons traveling at their invariant speed. Our understanding of the cosmos, from measuring the distances to stars to observing distant galaxies and cosmic microwave background radiation, depends entirely on the predictable behavior of photons. Their masslessness ensures that light travels consistently, allowing us to map the universe and explore it through observation with unmatched accuracy. Additionally, the massless nature of photons helps explain why they cannot be brought to rest in the conventional sense. Unlike a particle with mass, which can be slowed or stopped relative to an observer, photons always move at light speed in vacuum. This property also explains why we never observe a photon at rest, and why concepts such as the frame of reference of light are undefined. The absence of rest mass guarantees that photons are perpetually in motion, providing a constant standard against which velocities are measured and defining the ultimate limit for all matter and energy. In a more technical sense, the energy of a photon is determined entirely by its frequency, as described by the equation E equals hf, where h is Planck's constant and f is the frequency of the photon. This means that even though a photon has no rest mass, it carries momentum and energy, enabling it to interact with matter, exert pressure, and transmit information. These properties make photons indispensable to physics and cosmology, serving both as carriers of light and as fundamental participants in the interactions that govern the universe. Ultimately, photons demonstrate why the speed of light is not just a number, but a fundamental feature of reality. Their massless nature allows them to travel at this speed naturally, without acceleration, energy requirements, or the relativistic constraints that limit massive objects. They define the boundaries of space-time, maintain the consistency of causality, and provide the medium for the flow of information and energy across the cosmos. Without massless photons, the structure of the universe as we know it, including observation, communication, and energy transfer, would be radically different, and the cosmic speed limit would lose its practical significance. Massive objects, unlike photons, are bound by the rules of relativity in a way that fundamentally prevents them from reaching the speed of light. While photons are massless and travel at light speed naturally, Any particle or object with mass experiences increasing resistance as it accelerates. The faster an object with mass moves, the more energy is required to continue speeding it up. This is not a linear increase. As the object approaches the speed of light, the energy needed grows disproportionately, escalating toward infinity. No finite source of energy could ever supply this infinite amount, making it physically impossible for massive objects to reach or exceed light speed. The reason behind this lies in the very nature of mass and motion. Mass provides inertia, the property of an object that resists changes to its state of motion. As an object accelerates, its inertia effectively grows from the perspective of an outside observer. At everyday speeds, this effect is negligible and imperceptible, but at speeds approaching light, it becomes overwhelming. Even if one could harness all the energy available on Earth, or even from a star, it would never be sufficient to overcome the increasing inertia at relativistic speeds. The closer a massive object gets to light speed, the more stubbornly the universe resists further acceleration. This limitation is why no spaceship, particle, or physical object that has mass can ever break the cosmic speed barrier. Unlike photons, which are inherently designed to move at light speed without energy resistance, massive objects are fundamentally tethered to subluminal velocities. The universe enforces this rule to maintain consistency in causality, energy conservation, and the structure of spacetime. If massive objects could exceed light speed, the consequences would be profound and paradoxical. Energy requirements would become nonsensical. Cause and effect could reverse, and the fabric of reality could unravel in ways that defy observation and logic. Even in particle accelerators, where scientists propel electrons and other subatomic particles to speeds incredibly close to light, they never actually reach it. As the particles accelerate, their energy requirements skyrocket, and the closer they get to light speed, the less additional speed they gain for each increment of energy supplied. In practical terms, no matter how advanced our technology becomes, the approach toward light speed is asymptotic. Objects can get infinitesimally close, but they can never reach the limit. The universe sets this barrier as an absolute, ensuring that the laws of physics remain coherent. This distinction between massless and massive particles also illustrates why photons are uniquely capable of defining the universal speed limit. Photons glide effortlessly through spacetime at light speed, while massive objects are shackled by their mass and the inexorable increase in energy required to approach that limit. The contrast emphasizes a profound asymmetry in nature. Light sets the cosmic pace, while matter is forever constrained to lag behind, no matter how advanced the propulsion or how enormous the energy input. Moreover, this limitation has profound implications for human ambitions, such as interstellar travel. Even the most advanced spacecraft would be unable to reach the nearest star within a human lifetime if constrained to subluminal velocities, because the energy required to approach light speed becomes physically unattainable. It also highlights the practical reasons why science fiction depictions of faster-than-light travel rely on speculative mechanisms like warp drives or wormholes. The laws of physics make conventional acceleration to light speed impossible for anything with mass. In essence, the universe distinguishes sharply between massless particles and massive ones. Photons naturally occupy the top of the speed hierarchy, moving at light speed effortlessly, while massive objects are permanently limited by the ever-growing energy barrier that prevents them from catching up. The infinite energy requirement is not a technological problem. It is a fundamental physical law. This boundary ensures the integrity of spacetime, preserves causality, and defines a clear distinction between the speed of light and all subluminal motion. Experimental evidence from particle accelerators provides some of the most compelling proof that nothing with mass can reach the speed of light. Modern accelerators, such as the Large Hadron Collider, LHC, at CERN, are capable of propelling subatomic particles to speeds incredibly close to light speed. But no matter how much energy is injected, the particles never actually reach it. These experiments offer concrete, measurable confirmation of the relativistic predictions laid out by Einstein. As particles approach light speed, their effective mass increases and the energy required for further acceleration grows dramatically. Observing these phenomena in controlled laboratory conditions allows physicists to directly witness the principles that underpin the cosmic speed limit. In a particle accelerator, charged particles like protons or electrons are guided around a circular path by powerful magnetic fields while being accelerated by electric fields. As these particles gain speed, their relativistic mass increases. From the perspective of laboratory observers, each incremental boost in energy results in progressively smaller increases in velocity. For instance, an electron accelerated to 99.999% of light speed gains enormous amounts of kinetic energy, yet its velocity remains just shy of the ultimate limit. Even with the immense energies achievable in the LHC, no particle has ever been observed to reach or exceed light speed, demonstrating that the infinite energy requirement predicted by relativity is a real and unavoidable constraint. These experiments also provide a direct view of time dilation and length contraction in action. As particles accelerate to velocities approaching light speed, their decay rates are observed to slow relative to stationary observers. This effect has been measured in particles like muons, which naturally decay very quickly. When accelerated to near light speeds in accelerators, their apparent lifetime extends dramatically, allowing them to travel much farther than they would at low speeds. These observations match precise relativistic predictions, confirming that time behaves differently at extreme velocities. The measurements not only validate relativity, but also indirectly confirm the impossibility of surpassing light speed, because the very framework of time and energy changes in such a way that approaching the light speed barrier becomes progressively more difficult. Another critical piece of evidence comes from synchrotron radiation. When charged particles are accelerated along curved paths, they emit electromagnetic radiation due to their acceleration. The energy loss from this radiation increases steeply as the particles approach light speed, creating a natural resistance that makes achieving even higher velocities more and more energy intensive. This radiation loss is not merely a practical hurdle. It reflects the fundamental physical principle that as velocity increases, maintaining or increasing it requires disproportionate energy input. No matter how advanced the accelerator, these effects illustrate that the speed of light is a true physical boundary. High-energy cosmic rays also provide experimental support. Cosmic rays are naturally occurring subatomic particles that travel at speeds close to light. When these particles collide with Earth's atmosphere, they produce showers of secondary particles. By analyzing these interactions, physicists can determine the velocities of the incoming cosmic rays. Observations consistently show that while cosmic rays can achieve velocities incredibly close to light speed, they never exceed it. These natural high-energy experiments complement laboratory observations and reinforce the notion that light speed is an absolute limit, unaffected by the specific conditions or the method of acceleration. Particle accelerators also demonstrate the relativistic relationship between energy and momentum. As a particle approaches light speed, its momentum continues to increase dramatically, even though its velocity increases very little. This decoupling of momentum and velocity highlights the physical impossibility of reaching light speed. As the velocity asymptotically approaches the limit, the particle requires ever-increasing amounts of energy for ever smaller increments in speed. Laboratory measurements confirm this behavior with astonishing precision. For example, in the LHC, protons are accelerated to energies exceeding several tera-electron-volts, achieving velocities only infinitesimally below light speed. These results are consistent with the predictions of special relativity to many decimal places, providing overwhelming empirical evidence for the light speed ceiling. These experiments are not only fundamental tests of theory, but also practical demonstrations of why the cosmic speed limit matters for real-world physics. Every attempt to accelerate a particle illustrates the constraints imposed by relativity. The greater the velocity, the larger the energy demand, the more pronounced the time dilation, and the more extreme the effects of relativistic mass. None of these obstacles can be circumvented by conventional means. Even with all the technological power of modern accelerators, light speed remains a boundary that cannot be crossed. Furthermore, particle accelerators offer insights into phenomena that depend explicitly on particles moving close to light speed, such as the creation of exotic, short-lived particles. High-energy collisions produce massive particles that exist only for fractions of a second. The fact that these particles can be created, observed, and studied before decaying provides additional confirmation of relativistic time dilation and the impossibility of surpassing light speed. Every data point, every collision event, and every measurement of particle decay times serves as a testament to the universal applicability of the light speed limit. In addition to particle behavior, accelerators confirm that light itself acts as an immutable reference for speed. Instruments in these facilities consistently measure the speed of photons, and all relative velocities of accelerated particles remain below this universal benchmark. The comparison between massless photons and massive particles highlights the unique status of light. It is both the carrier of electromagnetic forces and the ultimate speed limit, while matter is permanently constrained to velocities less than this fundamental constant. Experimental observations also support the broader consequences of relativity for space travel and energy management. The enormous energy requirements for approaching light speed, the limits imposed by radiation loss, and the observed time dilation in fast-moving particles all reinforce the notion that human-scale or macroscopic objects cannot be accelerated to light speed. These results directly inform theoretical and practical considerations for high-speed travel, energy consumption, and the feasibility of interstellar exploration. Every particle accelerated in a laboratory is a microcosm of the broader cosmic principle. The universe enforces the light speed limit consistently across scales and contexts. Particle accelerators provide an unparalleled window into the physics of extreme velocities. Through careful control and observation, scientists can accelerate particles to near light speeds and measure the resulting relativistic effects with precision. These experiments confirm multiple aspects of relativity: increasing energy requirements, relativistic mass growth, time dilation, and the inevitability that no massive particle ever reaches light speed. Together with observations of cosmic rays and other high-energy phenomena, these data form a robust empirical foundation for the cosmic speed limit. Light speed is not a theoretical abstraction or a convenient number. It is a real, measurable boundary, consistently observed in controlled experiments and natural phenomena alike. The behavior of particles in accelerators reinforces the universality of this limit, demonstrating that nothing with mass can ever achieve or surpass the speed of light. The implications of the light speed limit for space travel are profound and fundamentally shape humanity's aspirations for interstellar exploration. While science fiction often portrays spacecraft traveling between stars in mere days or months, the reality dictated by physics is far less forgiving. The vast distances separating stars and galaxies combined with the unbreakable speed limit, create enormous temporal and energetic barriers that make interstellar travel one of the most daunting challenges imaginable. Even our nearest stellar neighbor, Proxima Centauri, is more than 4 light-years away, meaning that any signal or spacecraft traveling at subluminal speeds would require years to reach it. For macroscopic spacecraft with mass, accelerating close to light speed demands energy far beyond what we can currently produce, and even then, the journey would take decades or centuries from the perspective of an Earth-based observer. One of the immediate consequences of the speed limit is that timescales become enormously stretched for human travel. Even if we could develop propulsion systems capable of approaching a significant fraction of light speed, relativistic time dilation would alter the perception of time for the travelers. For instance, astronauts on a ship moving at 90% of light speed would experience time passing more slowly relative to people on Earth. While this effect could allow the crew to traverse vast distances in what feels like a reasonable time frame to them, decades could pass on Earth. This creates logistical and societal complications. Communication, supply chains, and mission planning become extraordinarily difficult when travelers are moving at relativistic speeds, because Earth-based observers age and change at a much faster rate than the crew in motion. The energetic requirements for near-light speed travel are staggering. As previously observed in particle accelerator experiments, as objects approach light speed, their relativistic mass increases, meaning more and more energy is needed to continue accelerating. Translating this principle to a spacecraft carrying hundreds or thousands of tons of mass highlights the practical impossibility of near-light speed travel with current or foreseeable technology. The energy sources required would need to be orders of magnitude greater than the combined output of all human power generation on Earth. Even speculative concepts like nuclear fusion propulsion or antimatter engines, while theoretically powerful, face enormous engineering and safety challenges and would still require decades or centuries to accelerate a sizable ship to near-light speed. Radiation and collision hazards also become increasingly severe at relativistic velocities. Space is not empty. Interstellar space contains dust, gas, cosmic rays, and other particles. At velocities approaching light speed, even a tiny dust grain can strike with catastrophic energy, equivalent to the detonation of a high-yield explosive. Shielding a spacecraft from such collisions while maintaining reasonable mass and energy efficiency presents an enormous engineering problem. The faster the ship goes, the more severe these hazards become, further emphasizing the practical limitations imposed by the speed of light. Communication is another significant constraint. Because information cannot travel faster than light, any messages sent to a crew on a near light speed journey will take years to arrive. For example, even at 99% of light speed, a message to a spacecraft traveling to Proxima Centauri would take more than 4 years to reach it. This delay renders real-time communication or coordination impossible, requiring missions to be highly autonomous or prepared for long periods of isolation. These limitations reinforce that the speed of light is not only a barrier to physical motion, but also a boundary for the transmission of knowledge, instructions, and coordination across interstellar distances. The physics of acceleration and deceleration also poses formidable problems. Even if a spacecraft could theoretically reach 99% of light speed, slowing down upon arrival at a distant star system would require similarly enormous energy expenditures. Unlike photons, which travel indefinitely without resistance, massive spacecraft must carry fuel or energy to decelerate, which increases mass and further amplifies the energy needed for acceleration. This creates a compounding problem. The faster you want to go, the more energy is required, and the more energy you carry, the more mass you must accelerate, which in turn increases the energy requirement. This feedback loop makes near light speed travel exponentially more difficult for any realistic spacecraft. Moreover, the longer duration of interstellar journeys relative to Earth time raises social and philosophical questions. Entire generations might pass on Earth while a single crew experiences only a fraction of that time due to relativistic time dilation. This separation creates profound challenges in mission planning, crew selection, and maintaining cultural and psychological continuity. Even if technological hurdles could be overcome, the human and societal dimensions of interstellar travel introduce additional layers of complexity that are inseparable from the constraints imposed by the speed of light. These challenges underscore why science fiction solutions, such as warp drives, wormholes, or teleportation, are so appealing. They circumvent the need to accelerate a massive object to light speed, while allowing for rapid traversal of cosmic distances. In reality, however, we remain bound by relativity. Every current concept for interstellar travel must contend with the immutable energy, time, and communication limits dictated by the speed of light. This does not make exploration impossible, but it makes true interstellar travel a long-term and multi-generational endeavor rather than a short-term technological feat. In addition to technical hurdles, the light speed barrier has practical consequences for exploration strategy. For instance, robotic probes and remote observation become far more feasible than human travel for initial exploration. Sending instruments, rather than people, allows us to gather data without the massive energetic and logistical burdens imposed by human requirements. Even traveling at a fraction of light speed, robotic missions can survey distant star systems, detect exoplanets, and study cosmic phenomena, demonstrating that while humans are constrained by relativistic limits, our technological proxies can extend our reach across the galaxy in a meaningful way. Ultimately, the implications of the light speed limit shape not just engineering considerations, but also our aspirations and strategies for interstellar exploration. Humanity's dreams of traveling to other stars must contend with immense distances, energy constraints, hazards, communication delays, and the relativistic stretching of time. These challenges make interstellar travel an ambitious, multi-generational goal that requires not just advanced propulsion, but also deep planning, ingenuity, and acceptance of the fundamental laws of the universe. The speed of light is more than a limit. It is a boundary that frames our ambitions, dictates the structure of space travel, and reminds us that even as our technology grows, the cosmos imposes rules that cannot be bypassed. The existence of a universal speed limit, the speed of light, carries profound philosophical implications, shaping not just the behavior of matter and energy, but our very understanding of reality. Unlike a technological constraint or a limitation imposed by current engineering capabilities, the light speed barrier is a fundamental property of the universe. It is woven into the fabric of space-time itself, defining the maximum rate at which cause and effect can propagate, the structure of information transfer, and the way energy interacts with matter. This limit suggests that reality has intrinsic boundaries, not in a punitive or arbitrary sense, but as an essential characteristic that ensures the coherence and stability of the cosmos. At its core, the speed of light links space and time into a unified continuum. Special relativity reveals that velocities near this limit distort both temporal and spatial measurements, meaning that time slows down and lengths contract for objects in motion relative to an observer. The very structure of reality becomes malleable as we approach light speed, yet these distortions are entirely consistent and predictable. The light speed limit, therefore, functions not merely as a boundary, but as a framework within which the universe operates. It ensures that events unfold in a causally coherent manner. Causes precede effects, signals travel at finite rates, and paradoxes are avoided. Without this constraint, the orderly sequence of events could break down, leading to contradictions that make reality itself incomprehensible. Philosophically, the speed limit also challenges human notions of freedom and possibility. Humanity has long been accustomed to the idea that effort and ingenuity can overcome obstacles, whether in exploration, invention, or survival. Yet, the universe imposes a constraint that no amount of ingenuity can bypass. Infinite energy would be required to accelerate massive objects to light speed, and even massless particles cannot transmit information faster than this limit. This limitation is not a technological barrier. It is a metaphysical one, embedded in the very laws that govern existence. It forces us to acknowledge that there are absolute ceilings to motion and communication, shaping the scope of what is possible, both physically and conceptually. The light speed limit also illuminates our understanding of causality and determinism. Because nothing can travel faster than light, information and influence are restricted to a finite domain, meaning that the universe maintains a consistent order of events. If the speed of light were different or could be violated, causal relationships could unravel, producing temporal paradoxes or inconsistencies where an effect could precede its cause. In this sense, the light speed limit is a guarantor of logical consistency in the cosmos. It underpins the very idea of time as a measurable and directional phenomenon, rather than a chaotic or arbitrary sequence. From a philosophical standpoint, this establishes a deep link between physical laws and the coherence of reality itself. Additionally, the cosmic speed limit highlights the asymmetry between human ambition and cosmic scales. Even as we advance technologically, even as we imagine spacecraft and probes that traverse vast distances, the universe imposes fundamental limits on how quickly we can move, communicate, or explore. This recognition can evoke a sense of humility. No matter how intelligent, resourceful, or determined we exist within a reality that has built-in restrictions. It also inspires a sense of wonder. The universe is not arbitrary, but finely structured, with limits that define its behavior and shape its evolution. The speed of light is one of the clearest manifestations of this cosmic order. On a deeper level, the speed of light connects to the nature of knowledge itself. All observations, measurements, and experiments rely on signals that propagate at or below this limit. In effect, the speed of light governs the ultimate rate at which information about the universe can reach us. This constraint implies that there are horizons beyond which we cannot observe or influence in real time. Light from distant galaxies takes billions of years to reach Earth, meaning that our view of the cosmos is always a glimpse of the past. Philosophically, this suggests that reality is not just structured by physical laws, but also by the finite ways in which we can interact with it. The speed limit shapes the boundaries of knowledge as much as the boundaries of motion. Furthermore, the cosmic speed limit emphasizes the special role of light and massless particles in defining the universe's architecture. Photons, moving precisely at this speed, delineate the limits of causality, provide the medium for information transfer, and structure the observation of distant phenomena. By contrast, massive objects are bound by subluminal velocities, highlighting a fundamental hierarchy in nature. This distinction reinforces the idea that the universe is not infinitely malleable, but organized according to precise, invariant principles that govern the behavior of energy, matter, space, and time. Ultimately, the speed of light serves as a profound philosophical boundary, a physical constant that embodies the interplay between possibility and limitation. It frames the architecture of the universe, governs the flow of time and information, and ensures the logical consistency of cause and effect. Accepting this limit is both a challenge and an invitation. It restricts what we can do in absolute terms, yet it reveals the elegance and coherence of the cosmos. The universe is not random or arbitrary. It is a precisely tuned system, in which the speed of light defines the boundaries within which all events, all motion, and all knowledge unfold. Light speed is more than a mere limit. It is a profound and defining feature of the universe, a constant that shapes the very nature of reality itself. From the tiniest subatomic particle to the largest galaxy, the speed of light governs how energy, matter, and information move, interact, and transform. It establishes the rhythm of the cosmos, dictating the flow of time, the sequence of cause and effect, and the structure of space across unimaginable distances. Every photon traveling through the vacuum, every signal sent from Earth to a distant probe, and every observation of a faraway star is bound by this universal constraint, making it the ultimate measure of motion and information in our universe. The elegance of the cosmic speed limit is mirrored in its universality. Light speed is invariant. It is the same for all observers, regardless of their motion or perspective. This invariance is central to our understanding of space and time, ensuring that the laws of physics remain consistent across the universe. It acts as a cosmic yardstick, allowing scientists to measure distances, velocities, and the evolution of celestial objects with incredible precision. Without this constant, our understanding of the universe would lose its coherence, and the predictability of natural laws would falter. The speed of light is thus both a boundary and a guide, a feature that defines how reality itself is experienced and understood. Moreover, the speed of light sets the stage for some of the most awe-inspiring phenomena in the cosmos. Time dilation and length contraction, observed at velocities approaching light speed, reveal a universe that behaves in ways that defy everyday intuition. The finite speed at which information travels gives rise to cosmic horizons, so that distant galaxies are not just far away in space, but are glimpses of the universe as it existed millions or even billions of years ago. These effects, dictated by the speed of light, remind us of the vastness and complexity of the cosmos and of the profound subtleties underlying what we perceive as reality. Even in human terms, the implications of light speed inspire wonder and humility. The fastest spacecraft we have ever built are still only fractions of the speed of light, making interstellar journeys measured in decades or centuries rather than years. The speed of light imposes fundamental limits on communication, exploration, and travel. Yet it also enables a consistent, ordered universe in which knowledge can be reliably transmitted and experiments can be meaningfully interpreted. It highlights the balance between constraint and possibility. While the light speed barrier prevents shortcuts, it provides the structure that allows the universe to function in a stable and comprehensible way. Photons, traveling effortlessly at this ultimate speed, carry energy and information across the cosmos, defining the boundaries of observation and interaction. Massive objects, bound by the relativistic increase of energy and inertia, underscore the universal nature of this limitation, contrasting with the freedom of light to traverse space unimpeded. These principles are not arbitrary. They are built into the very fabric of spacetime, demonstrating that the speed of light is not simply a feature of physics equations, but a fundamental aspect of existence itself. The cosmic speed limit also fuels our imagination and scientific curiosity. It challenges us to think creatively about how to explore, communicate, and understand a universe governed by such immutable laws. Concepts like warp drives, wormholes, and quantum entanglement, while still speculative, emerge directly from the recognition of light speed as the ultimate boundary. These ideas inspire not just technological ambition, but philosophical reflection on the limits and possibilities imposed by the universe. In the end, the speed of light is a reminder of the universe's profound order and its astonishing scope. It defines the pace at which events unfold, structures the sequence of cause and effect, and delineates the reach of knowledge and influence. It is a cosmic constant that touches everything, from the motion of galaxies to the heartbeat of a photon traveling across billions of light years. Light speed is a limit, yes, but it is also a window into the deeper architecture of reality, a principle that shapes space, time, and existence in ways both subtle and extraordinary. To understand the speed of light is to glimpse the underlying harmony of the cosmos, to appreciate the elegance of nature's laws, and to marvel at the universe's intricate and unfathomable beauty. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.